Alright, welcome to the tutorial video for the visisonics 564 panoramic audio video camera. I'm Adam O'Donovan, the CTO of visisonics, and we're going to go through the setup of the camera, how to use the software, how to use each one of the optional modules, both the VR and order tracking modules. So to start, I think we'll go through a little inventory of what you should have in the box. The first thing obviously is the camera. You'll have one audio video camera. You'll also have a tabletop tripod, so you can set it up in conference rooms. You'll have a power supply, a smaller brick, for the audio camera itself, a power supply for the computer, and a USB 3.0 cable. So the setup's actually very easy. You take the USB 3.0 cable, connect the B side to the USB 3 ports in the computer. Generally, the USB 3 port is the frontmost. We'll usually say SS for super speed, or it'll be blue. And then take the B side and connect it to the audio camera. The smaller brick, the power supply for the audio camera, just goes into the bottom port. The computer power supply obviously plugs into the computer. And if you have the optional VR module, your software will be compatible with the Oculus DK2. So the Oculus DK2 has two ports on it. One is a HDMI connector, the other is a USB 3 connector. If your computer doesn't have HDMI, we'll ship it with a converter so that you can connect HDMI directly to the computer. So for this, we'll connect the converter, and then we have a mini display port, connect that to the computer, and connect the USB to the USB 2.0 port. Once all of that's done, you're ready to power the camera, and we can start collecting data. Now that we've connected the camera and powered it, we're going to go through how to open the software, start capturing data, and analyzing data that you captured with the array. So on the desktop, you're going to see three programs. One is our main interface program. This is the VS Real Space. The other is a microphone array diagnostic and a video camera array diagnostic. These are tools that will help make sure that we're communicating properly with the camera before we do any recordings. So I'm going to click on the microphone array diagnostic. Here we just want to double check that the XEM3010 can be seen by the software. So here we know we're communicating with the central brain properly. And then we're going to double click on the video camera diagnostic. In the video camera diagnostic, we want to see 5 video cameras listed. There are 5 HD video cameras in the array. And we want to double check that the interface is USB 3.0. If it comes up as USB 2.0, there's a couple of reasons for that. One might be that you accidentally connected into a USB 2.0 port in the computer, in which case you can just swap it into the 3.0 and double check that the interface has come up as 3.0. Or the USB 3.0 might have devolved to 2.0, which can happen on occasion. If that's the case and you know you're plugged into the USB 3.0 port, and you just need to power cycle the camera to reload the USB 3.0 driver. So here we can see that everything is connected properly. Now we're going to run the main Real Space interface. So when we double click on the VS Real Space shortcut, we'll open up the main interface window. Here we're going to see a couple of controls. In the bottom left, you're going to see a green indicator. This means that we're still communicating well with the camera. If that goes red, it means the cable has come disconnected. You just want to run through the microphone and video camera diagnostic again to see where the fault has occurred. On the left knob here, we can see the analog gain setting of the microphone array. There are 3 gain settings, -20, 0, and +20, depending on how loud the environment that you want to record is. When set to 0, the saturation point is going to be around 118 dB SPL. So this is a good all-around setting for general environments that aren't too loud or aren't too quiet. If you're in a very loud environment, you can set the gain to -20. This will have a saturation point of around 128 dB SPL. And if you're in a very quiet environment, you can set it to +20. This will saturate around 98 dB SPL. On the right, we'll see the duration of the recording. So the recordings are fairly large, so what we'll do for the first test is we'll just do a 10-second sample recording. In order to get a recording session set up, we want to go to File, New Session. This will open up Session Directory. We'll do Test Session. And now you'll see that the capture button is enabled. For this test, I'm going to create a white noise with my cell phone, and then we'll image that in the post-analysis tool. So first I'll start a white noise generator, and we'll click the capture button. Now, as soon as the capture is finished and the data has been stored to disk, what we're going to see is a panoramic video pop up of what we've just recorded. Now, this is a program that is actually stitching the panorama from the 5 raw video camera feeds. So it's important that we let this program run to completion. If you close this program early, the raw data is still on the file, but you'll have to stitch the panoramic video later. So as soon as this capture is complete, this window will automatically close, and then we can begin analyzing that data. Now, once we've captured data, you'll see these buttons are enabled. The analysis is going to open up our main analysis window. In the main analysis window, we'll see a number of displays. The first is the actual panoramic video with an acoustic image overlaid on top. We'll have a color bar associated with this panoramic window that will show calibrated dB SPL levels for the selected region. We'll see a time domain plot for representative signal of what was just recorded. So here we can see the white noise, and then some speech at the end of the recording. And then we'll see a spectral representation. This spectrogram is going to show a spectrogram of whatever is in this red box. This red box can be clicked and dragged to anywhere within that recording to show us a spectral representation of what's going on. So if I select the speech at the end, we'll see each one of the speech energy regions. So the way that we go about analyzing the data is we select a region from within the data in the time domain. We then go into the spectral domain, and we can drag an arbitrary spectral temporal region over a piece of energy. And then we can compute audio image from the bottom right. In this case, my gain setting was set to +20. Then when we compute audio image, we'll be presented with the acoustic image associated with that instant in time. Here we've selected about a 100 millisecond window from 4.5K to 5.5K, from around the 2-second mark from within the recording. And what we can see is we can see the main hotspot associated with the cell phone, and we can also see a reflection off the table here. The controls in the center basically control how this image is going to be displayed. The right slider is the dynamic range. If we want pinpoint information about where that sound is coming from, we can slide the dynamic range to the minimum value of 1. This will show us that in fact that speaker on my phone is located right at the bottom of the phone. The left slider will show the maximum dB to be displayed. So if I slowly step this down, what we'll see is I'm lowering the max, so we begin to see saturation, but we get a little bit more information about the secondary reflections in the environment and the other sound sources. If I slide it up, we're increasing the maximum dB displayed, and you can see this color bar updating appropriately. And again, we can adjust the display settings this way. You can always click auto to rescale to default values. Now you can see that this panoramic video is Mercator projection, which means that the ceiling and the floor are stretched like on a map. If we want to see a more realistic projection, we can click on this top left toggle button. This is the spherical projection. The spherical projection maps it onto an actual three-dimensional sphere so that we can rotate around the image in a more natural way. Here we can see that the warp is much less. We can zoom in this image, we can rotate, and we can identify exactly where these sound sources are coming from. Additionally, if we want to look at a very high-speed movie of what's occurring in the dynamics of the field, we can select a temporal region. I'll look at the decay area of this white noise. Here we can see the impulse response of the room decaying. Then we can compute audio movie. So the audio movie is going to compute basically a 4,000 frame per second high-speed movie within the selected region. It takes a little bit longer to compute because for a short section like this we're computing several hundred acoustic images, but it gives you the ability to look at very, very fine temporal detail. Also, if you want to study the reverberant environment, this tool can be used to directly image the reflections in that environment. By making an impulse, you can watch each of these reflections occur in time. And so we'll see a little bit of that as we look through this decay. So once the audio movie is completed its computation, we'll see the audio image controls on the left here are enabled. There's a slider which indicates where in that movie we're going to be imaging. And now in the spectrogram you can see a thin red line. This thin red line indicates where the instantaneous image that is being displayed is currently located. So if I hit play, what we'll see is this high-speed dynamics. We see the reflected energy and the direct energy oscillating in intensity, and we see this red line moving forward throughout the data. Once we've turned off this white noise, we're going to start seeing only reflected energy as the energy begins to die down throughout the space. So we see reflections off the walls, reflections off the surface, and a pretty complex reverberant environment in this region. If we stop this, we can dial in to any point within that impulse response. Toward the end, you can see that now the only energy is along the walls. The energy from the ceiling and the floor has been absorbed. And again, for each one of these spots, we can look at the spherical projection as well. Now, the other tool that we have at our disposal is a beamformers. Beamformers are effectively highly directional microphones that we can compute for any possible look direction in this room. So we enable this beamforming mode by clicking on this virtual microphone icon. By default, you'll see it's showing a beamformer for every real microphone location. But what we'll do is we'll create a new beamformer file from the file menu. This will allow us to click in this image anywhere we like to generate an arbitrary number of highly directional virtual microphones. Each one of these microphone directions will generate a wave file that contains the isolated signal from that direction. So here I've added three, one for the main lobe, one for the reflection, and then one for a random spot in the environment. Now I can click Process Beamformers. It asks me to enter a prefix for these. I'll say beam test. And then it's going to compute these three wave files. In order to access these, I can either play them directly from the interface, or I can locate them in my session directory. So the session directory will always be located on volume V for visisonics. You'll have a visisonics folder, and then a sessions folder. This session is called test session, and in any session you'll see a test data and a beamform data. The test data holds all of the raw data, 64 wave channels, 5 video camera recordings, as well as the panoramic video. Anytime we've created beamformers, they'll be stored in the beamform session. So we added 3, so we can see we have 3 wave files associated with those beamformers. If I want to save the beamformer grid that I've created here for future batch processing so I can repeat this experiment over and over again, I can go here and click Save Beamformer File. I'll call this Test Beamformer File. And then that can be loaded on future sessions so that you don't need to click in the image each time. So I can load a test beamformer file, and we can see that these will be loaded directly in. If you want to output a current image, you can click on Reporting, Export Current Image. Again, it'll prompt you for a file name, test image, and it'll generate a high resolution image that can be used in reports. So one of the useful tools that comes with the audio camera is the real-time display. This is a real-time preview that allows you to look at the acoustic environment in real time, as well as analyze some of the acoustic characteristics. You can also preview, if you have the virtual reality module, you can preview the virtual reality mode with the Oculus DK2. So here in the real-time display, you see a panoramic video showing the entire scene captured. We'll also see an acoustic image overlaid on top of this video. So we can set this up in an environment, we can turn this on, and then we can see an instantaneous preview. I want to run through a couple of quick controls that you have. One is the stitch parameter. So if we look at some of these windows, they're not stitched properly. This is because of the stitch distance is set incorrectly for those objects. If By pressing O and P, I can set the stitch distance to be correct for the window here. Of course, now closer items won't be stitched properly. So the first step is often to choose, if you're in a small cabin, choose a correct stitch distance from within the real-time display. This stitch distance is going to be saved to disk and used for any future recordings that you make until you come back into this real-time display and reset the stitch distance. So there are a couple of things that you can do. One is you can listen to a real-time preview of a beamform signal. This red cursor will indicate where we want to listen to. It's effectively a highly directional virtual stethoscope. So if I hold it on my mouth, what I'm actually going to hear is a highly isolated version of my speech. I can take this and steer it anywhere around the room and listen to the sources that are coming from that particular direction. So in this example, what I'll do is I'll play a white noise source while I speak simultaneously. So now if I bounce back and forth between the white noise source and my mouth, you can see each one being emphasized one at a time. A, B, C, D, E, F, G, H, I, J, K, L, M, N, P, Q, R, S, T, U, V, W, X, Y. Additionally, if you've connected the Oculus DK2 and you have the virtual reality module, I can hit V, H, and R, and this puts it into Oculus Rift rendering mode. In this mode, my head will be tracked by the Oculus DK2, and I'll be able to watch exactly what was recorded or what's being recorded in it. Now, in addition to the beamformer mode, we also have a 3D sound mode. By pressing the B button, we'll toggle between 3D sound mode and the beamformer mode. In 3D sound mode, we render a spatially accurate representation of the sound field that was collected. This is useful in the VR module because it creates a really immersive environment. I'll go through a couple of the other controls within here. We're doing some temporal averaging. We can adjust that by pressing the plus and minus keys. That'll effectively increase temporal averaging or decrease temporal averaging. When it's decreased, we'll see that it's the instantaneous acoustic image is being displayed. So usually we want to look at some form of temporal averaging just so that it's a little bit more interpretable. So once I've set a stitch distance, I can escape from this, and now any recordings I make will utilize that stitch distance. So now the next step is, if we haven't computed a panorama or we want to recompute a panorama with a different stitch distance, what we can do is we can click the Export Panorama button. We can go into the test session that we've just created, test data. Here we can see we've already created a panorama, but I'm going to overwrite that. And once I hit save, it'll ask if we want to replace it, and I'll say yes. This will now relaunch the stitching program. With the new panorama settings, we can see now the stitch is corrected in the left corner. And it'll overwrite that session data. So in the event that we closed this program during the recording, this is how we would go about generating a new panorama. So first we'll go through the VR module. So the way to access this is through the analysis tool. If you have the VR module, this menu item will be enabled on your software. The VR module is very simple. Any recording that we've made, we can launch the VR playback directly to the HMD. Once I do this, we're going to compute our virtual reality parameters and then launch a virtual reality inspection program. This I can maximize, and now we can interact with the head-mounted display on that recording. So if, for instance, we've taken a recording inside a car cabin, we can then take that experience back into the lab, let somebody experience the audio-visual environment within the car over a head-mounted display and over headphones. In this, you have a lot of the same functionalities in the real-time display. So by default, we show the virtual reality mode, but if you press H and V, you can see the real-time acoustic image display as well. In this, you can click around, you can press B to toggle beamformers, and you can treat this as though you were interacting with the real-time display. Pressing escape closes it.